Start. Hello students, welcome to Talk on Civil Engineering. Let us discuss how we can design footings, that is isolated footing for the given data. So here you have a question. So here this footing is carrying a column size of 450 by 450 and it is carrying a load of 2300 kilonewtons and the safe bearing capacity of soil or soil bearing capacity. So it is 300 kilonewton per meter square. Okay. So for designing a footing, so you need to find out you need to determine three things. One is the size of footing. So you need to determine the size of footing. And the second one, you need to determine what is the depth or thickness of the footing. Thickness. And the third one, the reinforcement. So for any section, so for designing any footing section, these three things you need to find out. Okay. So for finding the size of footing, we'll be going to use what is the load carried by the footing and what is the area that is occupied or what is the bearing capacity of soil. Okay. So this size of footing will depends on the soil bearing capacity. Okay, the soil bearing capacity will influence the size of footing, and this thickness usually will be usually determined based on shear. The thickness will be based on the shear for footings. Okay, or else in other way you can find out the thickness using the moment. You can find the moment. You can find the thickness or the effective depth d required, or d you can provide d using the moment, and this d you have to check with the shear. అర్థమైందండి. సో థిక్నెస్ మనం షియర్ ని యూజ్ చేసుకొని థిక్నెస్ మనం ఫైండ్ అవుట్ చేస్తాం. సో డైరెక్ట్ షియర్ ఫార్ములాస్ యూజ్ చేసి అందులో నుంచి డి డిటర్మైన్ చేయొచ్చు, లేదంటే మూమెంట్ ఫార్ములా యూజ్ చేసి డి కనుక్కొని దట్ డి ఈజ్ సఫిషియంట్ ఫర్ షియర్ ఆర్ సేఫ్ అగైన్స్ షియర్ ఆర్ నాట్ అనేది చెక్ చేయొచ్చు. ఓకే, సో రిమెంబర్, సో ఇన్ టూ వేస్ యూ కెన్ ఫైండ్ అవుట్ ద థిక్నెస్, రైట్? But most suitable or most recommended one is shear. So మీరు shear design చేస్తే it will be accurate. So otherwise bending moment యూజ్ చేసి మీరు d కనుక్కున్నారు అనుకోండి, you have to increase that value. సో యూజువల్గా మీరు బెండింగ్ మూమెంట్ తో కనుక్కున్న వాల్యూ మీకు చాలా తక్కువ వాల్యూ వస్తుంది. సో ఆ తక్కువ వాల్యూ యూజ్ చేసినప్పుడు మీరు షియర్ లో సేఫ్ అవుతుండొచ్చు, అవ్వకపోతుండొచ్చు. కాబట్టి మీకు ఇక్కడ వచ్చిన వాల్యూకి జనరల్ గా మూమెంట్ యూజ్ చేస్తే వచ్చిన వాల్యూకి 2 times increase చేస్తాం. Okay, and coming to reinforcement, so this reinforcement will be based on the bending moment itself. So bending moment and the bending moment వచ్చిందో, so ఆ bending moment ki so IS 4561 provided one formula, right? So 0.87 fy ast d 1 minus fy ast divided by fck bd. So we will be using this formula to find out the reinforcement in the footing. Okay, so either square footing or rectangular footing, the procedure is just same, except the bending moment will changes. That's it. Okay, so if it is a square footing, so with respect to the column face, we'll consider the moments with the face of the column. So here this is your column. So at the face of the column, we'll consider the moment. So or if you take like this, so it will be like a cantilever beam. So this is your face of your column and this is your footing. So it looks like a cantilever beam. So since the cantilever will be same on all the sides, so for square footing, if you take movement about one direction, it's enough. For suppose if it is a rectangular one, so rectangular one means it looks something like this, right? So if it is a rectangular one, the cantilever portion will changes. So here this is a cantilever along the x direction, right? So here this L changes, and if you look at about y direction, this is your L, right? So here you will get two movements, movement about x direction and movement about y direction. You will see how we can find out the movement in this problem. But the basic difference between square or rectangle is just the movements. So you will get two movements in rectangle, whereas in square you will get only one movement. And in rectangle, since you are getting two movements, so the if you equate movement about x direction, you will get AST or steel required in x direction. If we equate the movement equation with y direction movement, so you'll get the AST with respect to y direction. That's it. Okay. And in case if you are providing thickness for in a rectangle, for a rectangular section, for a rectangular footing using movement, then you have to take, so you have to consider both the moments, and from both the moments, what is the maximum D required you are getting. So maximum D that you have to provide. That's it. Okay. Now let us jump into the problem. So as I told you, the first one is you need to find the size of footing. Okay. So let us find the size of footing. Size of footing. So in order to have a size of footing, we know that size of footing will get the size of footing by having the total load coming over the footing divided by soil bearing capacity. Okay, so here this total load in the sense, so you know the load is here, the load he has given is 2300 kilonewtons. Okay, and for this load we have to add the load of footing self weight as well as the backfill. Okay, so for that let us assume 10% of P has footing self weight and backfill weight. Okay, so the 10% of P will be how much? So 10% of P, so that is, so let us call it as self weight of footing as well as backfill also. Backfill also is equal to 10%. So that is 0.1 into 2300. So it will be 230 kilonewtons. Okay, and you know the P value is 2300, and total if you sum it up, it will be 2530 kilonewtons, right? Okay, so this is the total load. So this is the total load, right? And you know what is the SBC value? So SBC is equal to, it is given in the question, so it is 300 kilonewton per meter square. Okay, now just submit this substitute these values, you'll get the size of footing. So size of footing is equal to, the total load is 2530 divided by the soil bearing capacity is 300, so it will be around 8.44 meter square. Okay, so since it is here he is not mentioned whether it is square footing or rectangular footing, so how you will decide whether it is square footing or rectangular footing? So it depends on the size of column. So here your column is a square column, so it is much desirable to provide a square footing as well. Okay, so let us provide a square footing. So the size or side of square footing will be under root 8.44, right? So it will be around 2.9 meters. So let us provide 3 meters as a side of square. So here this is 3 meters. and this is also 3 meters. Clear? And this is the column, so it is 450. Right? So here the column size is footing size is determined. Now let us try to calculate what is the uplift pressure at the bottom of your footing. So uplift pressure in the sense, so if this is your footing, so below this footing you will have the pressure which is counteracting the load coming over the footing. Okay, so it will be counteracting this the total load, that is 2530 kilonewtons. So this uplift pressure, let us denote with QU. Okay, so uplift, so this is called net uplift. Net uplift pressure in the sense we are not including the self weight of footing. Okay, net uplift pressure. So this is net factored pressure. Okay, factored one, we are considering the factored one. So it will be QU is equal to 1.5 into 2300. So 2300 because we are not considering the footing self weight. That's the reason we are taking as 2300, and we are denoting with net uplift. Net in the sense it is excluding of self weight. So divided by the size of footing. So it is 3 into 3. So what is the formula? It is 1.5 into P divided by area of footing. Okay, so that is the formula, right? So now, okay, so let us, if you calculate this, it will come around 383.33 kilonewton per meter square. Okay, so this is your total uplift, net uplift pressure that is acting below the footing. Okay, so remember. Now let us go for the second case, that is the step 2. What is the step 2? We need to provide the thickness. Okay, so as I told you, you can provide the thickness in both ways. You can use the moment, you can use the bending moment, and to you can find out you can equate that bending moment with mu limit values. The bending moment equal to mu limit formula, and from this you can derive what is the effective depth, or else you can directly go to the shear concept, because in footings this thickness will be influenced or will be determined using shear itself. Okay, so this thickness will be based on the shear. So using shear to find the effective depth will be more accurate and more desirable. So let us use the shear concept to find out this effective thickness of the footing. Okay, right. So in footings you will have one-way shear and two-way shear. So let us firstly go to the two-way shear. So sorry, one-way shear. Usually this one-way shear will be more critical than the two-way shear. So coming to one-way shear, so you know how where the one-way shear will be acting. So if this is your footing, and here you having a column. So for one-way shear, the effective section will be from the face to a distance of d. So somewhere here. So this is your d. D is the effective depth of your footing. So this will be your area 3. So where the this is your critical section. Okay, so how you can find out this area, third area? Okay, so this will be so this is your let us call this let it be B here, and let this be L. Okay, and this dimension will be L minus A. So let us call it as A here. So this is A. So L minus A divided by 2. So it will be this portion, only this portion. You will get only this portion, right? And from this you need to deduct the D value, right? So it will be minus D. So now you will get only this portion. Okay, so this is this value. Okay, L minus A by 2. And from this, if you deduct D, so you'll get this shaded length, right? So now let us calculate what is the shear force, nominal shear force, VU1. So VU1 is equal to QU, the pressure, into area, A3. Okay, just force into area. Oh, sorry, stress into area, you'll get the force, right? So here area 3, let us elaborate this. So your A3 will be B, width is B, and the length is L minus A by 2 minus D, right? So let us substitute the values. So let me substitute this QU in terms of Newton per mm square. So if you convert this Newton into Newton per mm square, it will become 0.383 into B will be, what is your B value? It is 3000, and L is also 3000, minus, what is A value? A is 450 divided by 2. And what is the D? You know, we don't know the D, so we need to find out the D only. Okay, so if you simplify this value, so it will be around 0.383 into 3000. So this value will become 1275, I think, minus D. Okay, again, if you simplify this, it will become 14,64975 minus 1149 D. Okay, so this is your VU1. Okay, and we know that, so in order to save against shear, so this VU1 should be less than, or it is equal to VC1, or else it is nothing but this, your tau V should be less than or equal to tau C, right? Okay, the same thing. Okay, so this tau V is with respect to VU1 and this tau C with respect to VC1. Okay, so now let us find out the VC1. So in order to find out your VC1, we need to assume the percentage of steel, because we are going to use the table number 19 here. We are going to use table number 19 here. So in order to use table number 19, so here this is your table number 19, right? So in order to use this, you need the percentage of steel. You need the percentage of steel and the grade of concrete for which you are designing. So for footing, the grade of concrete is M20, and let us assume the percentage of steel has around 0.25. So for 0.25, what is the tau C value? So the tau C is 0.36. Remember this. Okay. So from table number 19, so assume percentage of steel has 0.25%, and we know it is M20 grade concrete, and the tau C value is 0.36. Okay, and how we have to find out this VC1? So we know that tau C is equal to VC, or shear force, divided by B into D. If you remember, this is the simple equation that we have been using to find out the shear stress, right? shear stress is equal to shear force divided by B into D, right? So from this we can find out the VC. So here VC1 is equal to tau C into B into D, right? So here your tau C is equal to 0.36 that we got from table number 19, and B, what is the B value? It is 3000, and we don't know the D, so we need to find out the D only. Okay, so this is your VC1. Okay, now we know that your VU1 should be less than or equal to VC1. Let us equate these two so that we'll get the D value. Okay, so what is the VC1 value? So VC1 is around 14,64975 minus 1149D. So this is your VU1. So it should be less than or equal to VC1. So VC1, if you multiply 0.36 in with 3000, it will be 1080D. Okay, so if you simplify this and if you're able to find out what is the D, so it will be D equal to it will be around 657 mm. 657 mm. So you can provide 660 mm. Okay, so this is your D required, effective depth required. And after this one-way shear, you have to go for two-way shear as well. You have to check whether this provided or this calculated effective depth is safe against two-way shear or not. Or else in other way, you can find out the other effective depth using this two-way shear as well, and you can compare these two values and what is the maximum one that you can provide. అర్థమైందండి? సో మనం వన్ వే షియర్ల నుండి మనం ఒక ఎఫెక్టివ్ డెప్త్ కనుక్కున్నాం. సిమిలర్గా సేమ్ ఇక్కడ కూడా సేమ్ కండిషన్, VU2 షుడ్ బి లెస్ దెన్ ఆర్ ఈక్వల్ టు VC2, సేమ్ కండిషన్ ఉంటుంది. ఇందులో నుంచి కూడా మీకు ఒక ఎఫెక్టివ్ డెప్త్ వస్తుంది. సో ఈ రెండిట్ల నుంచి వన్ వే షియర్ నుంచి వచ్చిన ఎఫెక్టివ్ డెప్త్, టూ వే షియర్ నుంచి వచ్చిన ఎఫెక్టివ్ డెప్త్ రెండు కంపేర్ చేసి ఏదైతే మాక్సిమం వాల్యూ ఉంటుందో అది ప్రొవైడ్ చేయాలి. యూజువల్గా జనరల్గా మాక్సిమం వన్ వే షియర్ నుంచి వచ్చిన ఎఫెక్టివ్ డెప్తే మాక్సిమం ఉంటుంది. ఓకే, ఆర్ ఎల్స్ ఇన్ అదర్ వే మీకు వన్ వే షియర్ లో వచ్చిన మాక్సిమం వన్ వే షియర్ లో వచ్చిన ఎఫెక్టివ్ డెప్త్ ని టూ వే షియర్ లో సబ్స్టిట్యూట్ చేసి సేఫా కాదా అనేది చెక్ చేసుకోవచ్చు, అలా కూడా చేసుకోవచ్చు. ఓకే, సో హియర్ విల్ చెక్ వెదర్ దిస్ D provided is safe or not. Okay, so and for two-way shear, the critical section, we need to know the critical section. Those are very important. So for a square footing, the critical section for a two-way shear is half of D. So here this is your half of D. The periphery, half of D periphery will be your critical section. So all this area you need to consider for finding VU2. Okay, so here you know this is your A and this will be your D by 2, and here this is also your D by 2, right? And this is your B and this is your L. Okay, now let us find out VU2 first. So VU2 is equal to, you know that the stress into the area. So here this is your A4, area 4. So A4 you need to consider. Okay, so what is the stress? It is 0.383, right? So into, so A4 is, so let us from a bigger area, let us subtract the small area, we'll get the shaded area, right? So that is B square minus A plus D. So D by 2 will become D, right? So A plus D whole square. So this is a formula, right? So now let us substitute all the values here. 0.383 into 3000 square minus A is 450 and D is 660 that we have calculated earlier. So this will comes to around 2975.12 kilonewton. Okay, so we got VU2 and let us find out VC2. So here VC2, we can calculate this VC2 from tau VC. Let us tau C2. What is tau C? How will calculate tau c? Shear force divided by area, right? So here the area, which area you need to consider? So here you need to consider the perimeter or periphery area. So periphery means perimeter into the depth, right? So the perimeter into depth. Okay, so this is your periphery. So this periphery area. Okay, so if you see in 3D, it looks something like this. Okay, so this is your periphery area. Okay, and you know this is this length, you know, so it is A plus D, right? Now let us calculate. This is VC2, so we need to find out VC2, not shear stress. So VC2 is equal to the formula will be K into tau C2 into perimeter into D. Okay, so here K will be the coefficient which will be calculated using Ks. So this is Ks is equal to 0.5 plus beta C. So this value should not be greater than 1. Okay, so and this beta C is nothing but the ratio between the column column shorter and long sides. Okay, so here beta C is equal to the ratio between shorter side of column divided by longer side of column. Okay, so here shorter and longer both are same, right? 450, so it will be 1. Okay, and your Ks will be Ks is equal to 0.5 plus 1, it will be 1.5. So but it should not be greater than 1. So therefore let us provide Ks has 1. Let us take Ks has 1. Okay, and what else we need to find? We got Ks and tau c. So here tau c, you'll get tau c using a formula provided by IS 456, that is 0.25 into under root FCK. Okay, so this is for limit state method. So we are using limit state method. So this is a formula. So it will be 0.25 under root. What is the FCK value? It is 20, right? So it will be around 1.118 kilo Newton per mm square. Okay, and what else we need? We got this value. You know what is a perimeter and D value. So let us substitute these values to find out VC2. So VC2 is equal to Ks is 1 into 1.118 into what is the perimeter? 4 times of A plus D, right? So what is A? A is 450 and D is 660, right? 4 times of 4 sides are there. 4 times of 450 plus 660. This is your perimeter into your depth, that is 660 as well. Okay, so we have substituted all the values, and if you calculate this, it will comes around 3276.818 kilonewtons. Okay, so here VU2 that you have calculated is less than VC2, right? So what is the VU2 value? It is 2975. So it is less than 3276. Therefore, whatever the depth you have provided, effective depth you have provided, that is okay. Okay, in other way you can keep D has undetermined at the till last వరకు D undetermined గా పెట్టేసి లాస్ట్ లో ఈక్వేట్ చేసి you can find out what is D and both maximum value provide చేయొచ్చు. So we know we got the effective depth as 660, and let us find out the overall depth. So for overall depth, let us assume the effective cover has 75. So here I'm assuming the effective cover as 75. This is your wish. So generally the nominal cover will be 50. For that I'm taking 25 extra, that's it. So it will be around 660 plus 660 plus 75, so it will be 375. 375 on the whole. Let me provide 750. So I'm providing 750 mm. 750 mm, and here you can again redistribute or rearrange this effective depth value as well. So from 750 you can subtract the 75, so it will be around 765, 775, or else you can calculate using the same value, that is 660. That is up to you, right? So with this we have finished. We have determined what is the thickness. So the total thickness is 750 mm, and effective thickness, effective depth is 660 mm. Okay, and what is the next step? So the next step is we have to find out the reinforcement. And remember, in case if you are finding this effective depth D value using the bending moment, that is 0.13 for F415 FCK BD square. So using this value, if you are finding this value, it will be very less. So that's the reason you have to multiply, or you have to take twice of this value, or more than twice of this value. For suppose నా ఇక్కడ ఈ ఫార్ములా యూజ్ చేసి అరౌండ్ నాకు 250 అలా వచ్చింది అనుకోండి, నేను ఏం చేస్తాను, 500 తీసుకుంటాను. ఓకే, సో 500 తీసుకున్నాక నేను మళ్ళీ షియర్ చెక్ చేస్తాను. షియర్లో సేఫ్ అవుతే ఇట్స్ ఓకే, కాకుంటే మళ్ళీ నేను ఇంక్రీజ్ చేయాల్సి వస్తుంది. ఓకే, రిమెంబర్ దట్. ఓకే, అండ్ నౌ లెట్స్ గో ఫర్ ద థర్డ్ స్టెప్, దట్ ఈస్ reinforcement calculation. So this reinforcement is based on the bending moment. So that is the reason first you have to find out the bending moment. Okay, so for the bending moment, the critical section will be at the face of your column. So for if this is a column, okay, so the face of your column will be your critical section. Okay, so if you see here, this looks like this looks like a cantilever, right? So it looks like something like this. It looks like a cantilever. It is fixed here, and underneath this you have a load QU. QU is acting here. So QU is equal to, you know that it is 383 kilonewtons. Okay, and this load, remember, this load is acting throughout the width. So it is acting throughout the width, something like this. So here you are having a column. So throughout this shaded region, this QU is acting. Remember. Okay, so let us calculate this. So firstly, let us find out the bending moment. So you know the bending moment is equal to, for a cantilever, it is QU, the load, into L square by 2. Okay, so it will be WL square by 2, right? So the L, so here this is your L. So how you can calculate this L? So from total B, if you subtract this column width, so you will left with only the width of footing. So from this you can take a half of the width, right? So that means, so this will be B minus A by 2. Okay, so B minus A by 2 will be your this value, right? Yeah, so B minus A by 2 will be that value, right? Correct. So this will be your value. Okay, so this is your B minus A by 2. Okay, now let us substitute these values, and this bending moment will be over the width B, remember. So this is over the B. Okay, now let us substitute all these values. So bending moment is equal to, what is QU? So it is 0.383. I'm substituting in newtons, and this value L will be 3000 minus A is 450 by 2 whole square divided by 2 into B is 3000, right? So if you simplify this, it will comes around 933.9 kilonewton meter. Okay, so we have calculated the moment. So what is the next step? We need to find out the area of steel. So how you can find out the area of steel? Just by equating this with the equation given in IS 456, that bend moment is equal to 0.87 Fy AST D 1 minus Fy into AST divided by FCK B into D. Okay, so here let us substitute all these values. So here moment is 933.9 into 10 to the power of 6 and 0.87 into 415 into AST we need to find out, and D is 660. 1 minus Fy is 415 and AST we need to find out 20. B is 3000 and D value is 660. Okay, so by solving this equation, so you'll get AST around 4094.8 mm square. Okay, so this is the AST you are getting, but we have assumed some value. If you remember, for finding tau c, we have assumed the percentage of steel has 0.25. So you have to check. So our design is based on this assumption. మనం డిజైన్ చేసిందంతా 0.25% ఆఫ్ స్టీల్ కి డిజైన్ చేసాం, కానీ మనకు వచ్చిన స్టీల్ 0.4094 వచ్చింది కదా. సో అది ఈ పర్సంటేజ్ కంటే ఎక్కువ ఉందా తక్కువ ఉందా అనేది మనం చెక్ చేసుకోవాలి. ఎక్కువ ఉంటే ఓకే, కానీ తక్కువ ఉంటే మనం అజ్యూమ్ చేసుకునేది ప్రొవైడ్ చేయాల్సి వస్తుంది. ఓకేనా? సో పర్సంటేజ్ ఆఫ్ స్టీల్ ప్రొవైడెడ్. So percentage of steel provided, how will get this value? So it is AST divided by B into D into 100, right? So AST is 4092.8 divided by B is 3000, D is 660 into 100. So it will be around 0.207. So which is less than 0.25%. So therefore, since it is lesser than what you have assumed, so therefore let us provide the assumed reinforcement. So therefore provide 0.25% of steel as reinforcement. Okay, so therefore AST required will be 0.25 divided by 100 into B into D. So it will be, so if you calculate this, it will comes around 4950 mm square. Okay, so 4950 mm square is provided in both the directions. If it is a rectangular, you will get two values in X direction and Y direction. That is the reference. Okay, so let us assume, let us provide a 16 mm dia bars, or you can take 10 mm dia bars also. So let us provide 16 mm dia bars since the AST is higher. 16 mm dia bars. So if you provide 16 mm dia bars, the spacing will be AST divided by capital AST into the width. So width is 3000. So this is nothing but your width. So throughout the width you need to distribute, right? So that's the reason I'm taking total width. So it will be around 121.8 mm. So I will take 120 center to center. Okay, so spacing, generally the spacing should be rounded to minimum value. Okay, so this is my spacing that I have provided. So at the end, my total reinforcement will be provide 16 mm dia at the rate of 120 center to center on both the sides. on both the sides. This is my AST. Okay, so at the end, so we have provided AST, steel we have provided, depth we have provided, as well as the area or the section, the area of footing. So at the end, you have to check for the bearing capacity also. So the fourth step, that is bearing or bearing pressure or stress distribution, you can call it as transfer, force transfer also, or transfer of forces. So okay, so for this case, so how we'll calculate this? So firstly, for this you need to find out the factored compressive force just below the column, compressive force at column base. So that will be, so it is factor, so 1.5 into 2300, so it will be 3450 kilonewtons. So this is the total load that is coming just below the column base. Okay, and now you have to find out the limiting or the maximum bearing stress, maximum bearing stress at column and footing interface. So at column and footing interface, what is the maximum or limiting bearing stress? So for that, so IS 456 has provided a few formulas. So if for a column, for the limiting bearing stress at column face, so the column face, the formula will be 0.45 FCK under root A1 by A2. Okay, so here A1 by A2, since it is a column face, so this is your column. So let us assume this is a column, and here this is your footing. Okay, so in column face, your A1 will be just below the column, and your A2 will be just above your footing. Okay, sorry, your A1 will be just above the footing. This is your A2, and your A1 will be just below the column. So that means your A1 and A2 both will be same, that is 450 into 450. Okay, so because we are considering just below the column face, and your this FSC is your column FSC, remember, not footing. So here he has, I think he has not mentioned about FSC whether it is column or footing. So let us take the FSC 20 M20 has M20 for the column as well. Column ki footing ki రెండిటికి M20 తీసేసుకుందాం. Okay, so it will be 0.45 FCK is 20 into under root, so it is 450 square by 450 square, so it will be around 9 Newton per mm square. Okay, so we have considered the column face. Now let us consider the footing face. Footing face. So footing face, in the sense, your A1 will be the footing, the area of footing above top of footing, and A2 will be the bottom column footing, sorry, the bottom column area. Okay, so the top footing top area A1 avutadi, column top column bottom area A2 avutadi. So remember that. Okay, so the formula is same, is equal to 0.45 into FCK. So here FCK will be the footing FCK into under root A1 by A2. So, and IS 456 is saying this A1 by A2 ratio, it should not be greater than 2. In case it is greater, you have to take 2. So let us check this value. I think it will be greater than 2. So A1 is 3000. So A1 will be your area of footing. So that is the reason I'm taking 3000 square. And A2 will be your area of column. It will be 450 square. It will be around 6.66. So it is greater than 2. So let us consider this. Let us consider this value has 2. Okay, so it will be 0.45 into 20 into 2, because IS 456 value under root A1 by A2 2 కంటే ఎక్కువ ఉండొద్దు అంటుంది, కాబట్టి 2 తీసుకుంటున్నాం. అర్థమైందా? So it will be around 18 Newton per mm square. Okay, so among these two, 1 and 2, what is the least value that will influence your design? Okay, so the least value is your column face, right? So therefore the column face governs the design. So let us see, based on the column face, how much force is being transferring. Okay, so therefore the limiting bearing resistance is equal to F, the bearing stress, into the area. So here we are, since your column face is governing the design, so you have to use column area. Okay, so it will be 9 into, so you have to use the column bearing stress 9 into 450 square. Okay, so it will be around 1822.5 kilonewtons, so which is less than what is the bearing stress, or what is the bearing force, or the compressive force. We have calculated the compressive force, right? So it is 3450 kilonewtons, the factored compressive force below the column. Okay, so it is less than that value, so therefore you need to provide some excess reinforcement, you need to provide some excess bars in order to distribute this force. Okay, so what is the excess force? So the excess force is equal to 3450 minus 1822.5, so it will be 1628 kilonewtons. So this 1628 kilonewtons is transferred using, so just at the end you can write a statement, that is enough. So this excess force can be transferred using dowel bars and extending column reinforcement or column bars into footing. So by extending the column reinforcement into footing, and even in bending that and providing a bend of 90 degree bend, you can distribute this excess force. Okay, so that is enough. Okay, so that means how will be my cross section of footing cross section? So this is my footing, a rough, I'm drawing with rough figure. Okay. Okay, so the depth the overall depth is 750 and my effective depth is 660. Okay, and steel, this is my steel on one direction, and above this you have steel on other direction. Okay, so this is my 16 mm dia at 120 center to center. Okay, and the steel which is coming from column, it should be bent in 90 degrees bent in order to distribute that excess force. Okay, and sufficient development length needs to be provided. Okay, right. So this is my column, square isolated column design. Okay, if it is a rectangular column, I have told you what is the difference, so just follow that value, that's enough. Even if it is sloped also, the difference will be where you are in critical sections. So the critical section is at D, a critical section is D by 2, you are taking for one way and two way shear, right? So one way two way ki critical section ela తీసుకుంటున్నామో only అందులోనే difference వస్తుంది. So D దగ్గర critical section అంటే మీరు you have to take the depth at D. Okay, D by 2 అంటే క్రిటికల్ సెక్షన్ d/2 దగ్గర అంటే d/2 దగ్గర ఎంత డెప్త్ ఉందో ఆ డెప్త్ తీసుకోవాలి, అంతే డిఫరెన్స్. ఓకే, so if possible I will discuss sloped section as well in the next video lecture. Thank you all.